So it got 4 pi v nu, and nu square, 4 pi v nu square d nu by v cube. I think that is what it is. Okay, so omega k. Now what we consider as that, suppose this is the case for a particular mode with frequency nu. Now these types of frequency, a particular frequency wave, now we are considering a three-dimensional crystal, for example. Okay, so three-dimensional crystal. Now in that case there can be for a particular wave moving in this particular direction, which is the direction of the wave vector k, and that can be in x, y and z direction. So now suppose that wave is like this. This can be one wave, that is translation transverse direction, the oscillations the amplitude in this direction, or it can be in this direction, right? Or it can be like this, so that there can be two transverse wave and one longitudinal wave. And the velocity in principle in transverse direction, if it is a homogeneous crystal, then it can be same, or it can be different depending on the crystal structure. That velocity in the longitudinal direction is different from velocity in the transverse direction. Now considering that the transverse direction velocities are depending on the kinds of structure, let us consider in both direction, this way or this way, are same, and the longitudinal wave velocity is different, and in that case this in general, that this can be represented, actually this function can be represented as g nu d nu now in terms of nu expressed. Okay, now this, the Debye expression finally for g nu d nu comes by taking consideration of the fact that each such wave can have same frequency but the directions may be different. So it's kind of contribution coming from two part of contribution coming from the transverse wave and one part coming from the longitudinal wave. So three such type of possibilities leading to nu square d nu. So this is the essentially the final Debye expression for g nu d nu. And then for convenience, what Debye did is actually considered an average velocity in three directions being same. So v0 he considered as an average velocity of the standing wave being same. Considering that, it becomes essentially 3 by v0, so essentially 3 times of that, and then that g nu d nu ultimately becomes for Debye is basically 12 pi v nu square d nu divided by v0 cube. So the long wavelengths that happens because of these concerted motion of these vibrations of all those atoms in their respective lattice positions, that leads to an estimation of g nu d nu, which has got this kind of behavior for frequencies between nu and nu plus d nu. So this is associated with nu and nu plus d nu. Okay, now given this, we have to again follow the same rule. Same rule means that you can have only 3n number of vibrations. So Debye, once you consider that this kind of frequency dependence is there for this g nu d nu, he also has to satisfy one equation. So that means he considered that there can be at the most, there is a maximum value of frequency. It cannot just go on increasing up to infinity. So being really realistic, so Debye thought that a maximum, it can go from 0 and go up to a maximum limit of frequency depending on the characteristics of the crystal. And then he has to satisfy one particular condition, that if you consider the integration of this g nu d nu, that cannot be violated. So that must be equals to 3n, actually 3n minus 6, but for all practical purposes 3n when n is very large. And that when you put that nu square d nu, ultimately this function comes as 4 pi v nu d cube by v0 cube. So this is the condition, rather this one, 3n equals to this, that will give you an estimate of the nu d, which is the maximum frequency of these normal vibrational modes, long wavelength vibrational modes, which are possible in Debye model. And that automatically nu d you can solve from here, and that comes as 3n by 4 pi v to the power 1/3 and v0. Okay, so this gives you an estimate of the nu d value, and that nu d is defined as Debye frequency. So we'll come to this Debye frequency definition, and we'll start from here next.